dust that are in the Milky Way towards Sagittarius. So Sagittarius A asterisk, or also called Sagittarius A star, is the name of the central black hole of our Milky Way galaxy. And it's right in the center, and so it's surrounded by a giant um, a number of stars. And looking in that direction, the Milky Way is just littered with dust and photogenic things. But you have to be able to see the southern horizon to do that. Yeah. Hi, Carson. Uh, yeah, for you. Well, the comfy chairs are mostly over here, unless you want to sit in the front, which nobody does because I don't know. Maybe maybe I spit when I talk or something. Oh, wow. All right. Another minute or two. A smaller turnout today. That's all right. You guys get the best science program of the month. Well, I don't know. I don't know what Mike's going to do in a couple weeks. I'm not sure that Mike knows what he's doing in a couple weeks. Yeah. All right. So I was first. I want to thank the church for providing the logistics, the microphones and the projectors and the seating and the climate control and all of these things that make it conducive to having us gather here. And the Unitarian Universalist denomination has a particular affinity for stories we can tell about the way the world works and why things are the way they are, etc. And so it's one of the few, I can think of maybe one other, one of the few um, sort of religious denominations that originate from Christianity that embraces science. And I'm a science geek. I'm a lifelong science learner, and for the past 12 years or so, a science educator here. And so we talk about science here, and we welcome you. If you are interested in science and topics from spirituality to non spirituality and agnosticism or atheism or humanism or Buddhism or essentialism, whatever your spiritual or intellectual path is, hopefully you'll find a community of, of people here that welcome you. And I welcome you to Science Sunday. So I was going to make this presentation. I was talking to my husband, who's back there at the AV Center. I had this idea of making a Science Sunday about basic questions. Why is the ocean salty? Why is the sky dark at night? Um, why do things, I don't know, roll downhill? I mean, just basic stuff that you might encounter from a 9-year-old, right? And what is the science behind it? Maybe we've all encountered answers to these things over time, but maybe we've forgotten some of them, and maybe there are questions we have about the way the world works that we just have in our adulthood, we just accept. Oh, yeah, the sky's blue. It's always blue. It's the way it's supposed to be. Well, so I was going to make a presentation all about these sort of basic questions we have about nature and the world around us that come up as we're growing up and as we observe the world. And I started writing up something about why the sky is blue. And then I thought, well, it's not always blue. I mean, sometimes, like especially during sunsets and sunrises, we get these colors. And then sometimes at night, instead of being black, the sky is illuminated by lightning or by aurora. And it occurred to me that I could do an entire presentation just about things we see in the sky that aren't specifically astronomical objects like, the sun and the moon and stars and whatnot. So I've made up this presentation, I hope you enjoy it, about things we see in our sky. And hopefully I can get this clicker to work. I wonder if the battery's dead in this. The laser worked. Yeah. I don't I don't know if the dongle. Oh, there it goes. All right. Yeah. Well, the computer that controls it's way back there. Yeah. So part one, the atmosphere and light, specifically light. So let's talk about interesting things that happen with regard to light and the atmosphere. So why are skies blue? How many of you are pretty confident that you know the answer to that? Oh, good, good. So skies are blue because there's blue light that comes from the sun. And there's also red light and green light and yellow light. And if you're out in space, on the moon, which has a very thin atmosphere, mostly of argon, I think. But if you're on the moon or way up in the upper atmosphere, orbiting in the space station, which is in the atmosphere technically, um, but if you're above the bulk of our atmosphere, the sky looks black, even during the daylight. And if you were to look at the sun while you were up there, which I don't advise, but you'll learn that during your astronaut training. If you were to look at the sun, you would perceive its color as white, right? And remember Isaac Newton with his prism splitting a beam of white light into Roy G. Biv, right? And so, why is the sky blue? If the sun emits all the colors of the spectrum, then why isn't the sun or why isn't the sky white, for example? Why is it blue? Well, it's because that uh, molecules in our atmosphere that are very plentiful, especially nitrogen, which makes up about 78%, and then oxygen, which is 21%. I think so. So those two together are often diatomic, right? They couple together two oxygens and two nitrogens, and the coupling of those atoms to make the molecules happens to create entities that are about the same size as a wavelength of blue light. And so the blue light hits them and it gets kind of discombobulated and it goes off in another direction, right? The atoms don't permanently absorb the light when it hits them. They almost spontaneously re-emit it, but re-emit it in a cockamamie direction. And so this is called scattering. And it's the scattering of specifically the blue light that comes from our sun that causes the sky to look blue. Now, have you also noticed that it's particularly blue up at the zenith, straight up, and it kind of gets paler as you look towards the horizon? Well, that's also because of scattering. Come on. But it's a different kind of scattering. So the kind of scattering that makes the sky blue is named Rayleigh scattering after the gentleman who first characterized the science behind it back in I think the late 17th, late 18th, early 19th century. Um, and it's particles that are um, on the size of or smaller than the wavelength of the light. So that's the molecules I was talking about. Let's see. And the blue light is scattered more than the other colors. Right, and like I said, if you're out in space, the sky looks dark, even though the sun may be right there in your field of view, like it is in this beautiful picture of the sun peeking over the limb of the Earth. And so it's the fact that we have plentiful gases in our atmosphere that take that light from the sun, and instead of having a black sky where you could see the sun and potentially other stars during the day, instead the blue light is scattered all over the air, all over through the envelope of air over our heads, and we see the blue light. All right, so there's another kind of scattering that has to do with why it looks white or lighter colored toward white on the horizon. And if I go back to that picture a moment ago, especially this one, you can see that effect, right? So it not only gets kind of a duller blue as you get towards the horizon, but it tends towards white. Well, that phenomena is the same phenomena why clouds are white. But we don't always see white clouds and blue sky, particularly at sunrise and sunset. So why, now that you know why the sky is blue, can you suss out why the sky may look red and the sun may look red or orange during sunset? Anybody have a theory about that? A hypothesis? Sort of like a prism, okay? So the notion is that the light may be refracted like it's going through a prism. And we only see, like you see the Roy-G-Biv, red, green, blue, indigo, violet, ultraviolet, right? That's Roy-G-Biv is the mnemonic to help remember that. So maybe the atmosphere is acting like a prism. It's a good suggestion. Well, it turns out that what happens instead, it was a great suggestion. It turns out not to be consonant with reality, however. Like many of our ideas that we have, we end up being wrong. Yeah. So the sky looks red during sunset because the blue light has been scattered out. The blue light in this picture, if this is, let's say it's a sunrise, right? The blue light's busy being in Finland right now. If this is a picture over Lake Michigan or something at sunrise, the blue light's over there in Finland and in the Atlantic. And by the time the light gets to us, it has traveled through so much atmosphere. So when you look up straight, you're only looking through, 10 miles or so of atmosphere, give or take, depending on the optical extinction path length, etc. But when you look up, you're looking through a relatively thin amount of atmosphere compared to the amount of atmosphere when you look towards the horizon. You've got miles and miles, tens, hundreds of miles worth of atmosphere that you're looking through when you're looking on the horizon. And when the sun is near the horizon, or the moon sometimes, when they're near the horizon, the blue light that gets emitted by the sun or scattered by the moon, that blue light has been filtered out, essentially. So the atmosphere works like a light filter. So the blue light is gone. It's been scattered by the atmosphere on the other side of the world, on the other side of the horizon, largely, by the time the light gets to you. And so what's left, if you take away blue from white light, you're left with reddish orange, right? So that's why the sun looks more orange or red during a sunset. And then when we add to that the fact that our atmosphere is usually full of water vapor, so clouds are not vapor. The part of clouds you see are not vapor. The part of clouds you see are microscopic water droplets. And the reason clouds are white is because of me. So I'll take your congratulations later. Yep. Clouds are white because of me scattering specifically. M-I-E is the name of that scattering. Some of you have heard of Rayleigh scattering when you were in junior high science, probably, but you may not have heard of me scattering. In fact, I don't remember learning this in college or in primary school. I learned this week as I was preparing for this talk. And I was grateful to learn that it was because of me. So, me scattering entails light interacting with particles that are about the same size or just a little bit larger than the wavelengths of light. And what those do is they effectively scatter all of the colors of light. Well, if you're scattering all the colors that are in a prismatic beam of light that's Roy-G-Biv, you're scattering white. Well, this is the same reason clouds look white. It's the same reason that the horizon looks white. Remember that picture I showed you a couple of times? If you look towards the horizon, it kind of goes towards a white or a gray, or depending upon the pollutants, if you're talking about ozone or maybe forest fires or other kinds of pollution, you can get an orange or a yellow tint to it as well, even during the daylight at the horizon. And that's because of the thickness, the path length. That's a technical scientific term for how far the light has come to get to your eyes. The optical path length is so great when you're looking towards the horizon that it gets scattered even by relatively rare water droplets that exist in the atmosphere, microscopic water droplets that are there even on a clear day. So even if there are no clouds overhead to look white, when you look at the horizon, you're still looking through an atmosphere that is loaded typically with a certain amount of water and water droplets. And those water droplets, not the water molecules, but the little condensates, the tiny droplets that have a little piece of dust or a piece of bacterium or a piece of human skin cell flakes or whatever, the little piece of dust that form an ice crystal or a water droplet, those scatter white light. Now, this is the same phenomena that makes snow white, that makes sea foam white. Anytime you get particles that constitute a bulk, and the individual particles are roughly 1.5 or so times the wavelength of the incident light, they'll just scatter it. And that's why clouds look white most of the time, except during sunset. Well, during sunsets, it, the clouds and the atmosphere don't have blue light to operate on. The blue light's been taken out, it's been filtered out. So when you only have red and orange and yellow and green, the sky rarely looks green, but in any case, when you take the blue light out, then you're left with these pastel colors. And it's these pastel colors that we perceive on the horizon, especially if there's a lot of pollutants in the air. You'll notice that during periods that you've lived through when there's been a lot of volcanic activity in the world somewhere, or when there are a lot of forest fires. Remember the past few years, occasionally there have been these gargantuan forest fires in Canada, and that makes for pretty sunsets and pretty sunrises, right? Because the particles of smoke that are floating around in the atmosphere are enough to scatter and sometimes to preferentially color some of the light. They act as their own kind of light filter. So the colors we see at sunset are because the blue light's been taken away and we only have the red and orange to work with. And that's also, you'll notice that the clouds are red and orange, right? Because that's the color of the light they have to work with. They're no longer working with white light, so they don't look white anymore. That make sense? And they're beautiful. Yeah. During sunsets, Mie scattering causes the sky to appear pastel due to the scattering of light by atmospheric particles. Now, the exact color depends upon the composition and the relative sizes of the dust particles or water droplets, etc., or the pollutants that are causing the scattering. All right. And it can be, obviously quite just awesome, right? One of the most beautiful spectacles of nature is a gorgeous sunrise or a gorgeous sunset. And I think was it Keats who said something about accusing scientists of unweaving the rainbow, right? Like, well, now we understand why it happened, so it doesn't have to look beautiful to us anymore. Well, that's nonsense, right? It's still gorgeous. And we'll talk about rainbows in a minute, by the way. All right, this is a picture taken by my husband just the other day of a beautiful clear sky. Uh, right, yeah. And I've used Photoshop to remove the light poles that were obscuring our view of the sky here. And here we see Rayleigh scattering causing the blue dome of the sky, and Mie scattering, which causes the horizon to look milky, right? So two kinds of scattering. And if you look carefully, you'll see, come on. I don't know why this is giving me such hassle today. There. Okay. If you look carefully, you see an airplane and a contrail. Contrails are condensed water, typically. One of the primary exhaust components of burning hydrocarbons is a lot of water. And so the water droplets up in the upper atmosphere form these contrails, not chemtrails. Chemtrails are pseudoscientific bollocks. But anyway, it's the same. The contrail left by the water droplets in the exhaust from the jet engines is white for the exact same reason that clouds of any sort are white. So several atmospheric phenomena visible here in a perfectly clear sky, which otherwise might be unremarkable except for being pleasant. All right, let's talk about rainbows. So, rainbows, those water droplets I was talking about, they're ubiquitous in the atmosphere usually, and they're particularly ubiquitous during a relatively rare phenomena we call rain. I don't know if you've experienced that in the past month or so, but during rain showers, the water droplets are big enough, right? So that's kind of what rain is. It's the microscopic droplets in clouds, and they get together because of cohesion and other electrostatic forces and whatnot acting on them, and eventually they can become stuck together enough that they overcome the lofting effect of the heat of the atmosphere and wind, and they fall as rain. But you'll notice one of the things you'll notice here is that the clouds no longer look white, largely, right? They're dark, they're gray. Well, that's one of the things that happens during a thunderstorm or on a particularly cloudy day is that the clouds don't look white. Well, I just got finished telling you that clouds are white because of me scattering. Why do they look gray? Well, eventually, if you scatter out all the light, and there is a little bit of absorption that goes along with it, the intensity of the light diminishes to the point where it looks gray. So white and gray are on the same literal spectrum, right? They're just different light intensities of the same all colors kind of phenomena. But if you get droplets of water that are larger than microscopic, then they act like tiny little lenses. And you get trillions of these lenses floating through the sky. And one of the things that happens in there is internal reflection. So back to Newton and his prism, the reason Newton's prism worked, what would happen if Newton held a flat plane of glass, just a little cube or a little prism? Prism is a geometric term for any kind of shape that's three-dimensional, but just a little plate of glass. If you hold that up to a white beam of light, the white beam of light just goes straight through it, right? Actually, it diffracts a little bit, right? If you look at it carefully, it's kind of like, putting a ruler or a pencil into a glass of water, and you see that diffraction causes the image to bend a little bit, the optical image. Well, that's because other mediums cause light to deflect, right? Well, it turns out that not every frequency or color of light deflects by the same amount in a given medium. Some colors reflect more at a bigger angle than other colors. And if you've got a prism, then that accentuates or amplifies that effect because the amount of material that the light is traveling through changes based upon whether you're at the tip of the prism or down near the body, the thicker part of the prism, of the triangle. And so that change in the thickness of the medium the light is going through amplifies the effect of the dispersion. That's called the dispersion of light due to diffraction. Well, inside the rainbow, the rain droplets, you've got white light coming in and hitting, and it hits one edge of the rain droplet. And if it hits that edge of a rain droplet at a particular, it's called an acute, it's from Snell's law, a particular angle, then it gets a perfect reflection. So the light comes in and it reflects out. But the angle at which it reflects is due to the properties of the water, the refractive index of the water, and also the wavelength of light. So the light gets dispersed when it's reflected out of these raindrops. So it comes in, it hits the raindrop, and it's reflected back at your eyes. So here's another opportunity for you to use your awesome powers of human deductive reasoning. If the rainbow is reflected light, which it is, that means the light must be coming from where in order for you to see a rainbow? Behind you. Excellent. So here's what I know. Whenever a rainstorm or a squall comes through and passes my house during the spring or fall or any time of year, February, I don't know, global warming, could happen. Anyway, when a rain squall comes and goes, if the sun is overhead, then where would the rainbow be? Under your feet. Well, there are no water droplets scattering light under your feet, right? So in order for you to see a rainbow, there have to be water droplets that are in a line between the sun, your eyeballs, and the rain. And that's why you see rainbows during the early morning or late afternoon, is because the sun has to be low on the horizon. So a rain squall comes by my house, and then I see sunlight. My husband could tell you that one of the things I typically do is I drop whatever I'm doing and I run to the door and I look on the opposite side of the sky as where the sun is. Because you can predict where a rainbow happens. You can predict when it happens. As long as the sun is low on the horizon and a squall has passed you by, go outside and look opposite to where the sun is, and you will have a great chance of seeing a rainbow. And here's some diagrams explaining that. And one of the things that can happen is the light can bounce twice inside a raindrop. And when it bounces twice, it's absorbed more, right? So along the way, the light is absorbed by the water in the raindrop. And so it's dimmer, less intensity of light from the second reflection. So you will typically see, if the sunlight is bright enough, you will see very dimly a second rainbow. It's called a secondary rainbow, and that's because of two reflections and refractions and dispersions, all of this science, in the raindrops. And you can see how this works here. Any questions about this before I go on? Yeah, Joanne, can you use the microphone to help with our questioners? Dave, is the microphone registering?
I was wondering why the rainbows are curved. Are all rainbows throughout the planet always have the same arc? And are we saying that arc is somehow proportional to the size of the sun?
That's a great question. So the size of the rainbow and the extent of it in the sky is related to how the relative sizes of the raindrops. So bigger raindrops and tinier raindrops. You'll see a little bit of a change in the size of the rainbow, and you may see obviously a partial rainbow. When you look at a waterfall or a garden hose, right, when you're spraying it out, you'll see colors in it that have the same kind of radius of curvature, consistent with that size of water particle that you're making in the spray from the water. Another question?
Yeah, can snow also cause rainbows? Or is that?
Can snow cause rainbows? I don't think so. There are other things that ice crystals do, and I'm going to talk about that in a minute, though. So I'll give you your $5 later. All right, one of the other things you'll notice in a rainbow is that inside the primary arch of the rainbow, the sky may look brighter. And that's because of the way the white, what essentially is the white light, is concentrated, like kind of like through a lens. It doesn't magnify, but it increases the brightness of the light inside the rainbow. So here's some of the answer, Karsten, to the question you answer about viewing angles and observer perspective. The angle at which the observer views the raindrops affects the location and size of the rainbow. The observer can see a full 360 degree if you're actually high enough. So if you're in an airplane, sometimes you may have seen this, you look down at the clouds, which are water droplets. If you're flying in an airplane, sometimes you look down and you actually see a bow, a circle, a prismatic circle. And it's the same phenomenon.
Wait. Sorry. It looks like it's hitting the ground, but is it actually continuing somewhere else in the world?
Not really. I mean, the tendency is to form a complete ring, but the ring, in order for it to be visible to your eye, remember your eye has to be in a line from the sun to the water droplets. You have to, in order to see the complete ring, you'd have to be above the water droplets, and that's why you can see a complete ring if you're in an airplane. I don't know this for certain. I didn't look it up, but I suspect that if you're high on a mountain, you know, sometimes you're above the clouds in a mountain, and maybe if you look down, maybe you can see a ring in the clouds. But even if you look down and see a rainbow, I'm just thinking about it out loud. I'm up on a mountain, the sun is behind me, and the water droplets are down here. Well, the water droplets, that would still be close to the ground. There'd still be a ground horizon in the sky. So I think it would still be a bow, even if you're up high on a mountain. You kind of have to be literally above the water, where the sun is coming from behind your head, but you're also looking down at the water droplets. And to look down at water droplets, you have to be between the sun and the water droplets, and it's rare that you get into that situation.
I read somewhere that there's actually 3 rainbows, but only under the most ideal conditions can we sometimes see the third one. Is that true?
Yeah. So you can have multiple internal reflections in a raindrop. Typically, we just see the effects of one, the primary reflection. The second one causes a secondary rainbow, and there's a tertiary one that occasionally happens. But so much of the light in the raindrop has been scattered by the first couple of reflections or absorbed by the water molecules that and scattered by me scattering, etc., that it's really rare that you're going to see a third rainbow. And I don't know enough to tell you what specific conditions to look for, but we can probably use Google for that.
Phyllis and I saw it once.
You saw a triple rainbow once?
Triple rainbow once, and we went,
Yeah. The fact that you know about reflection and refraction, did that just ruin the experience for you?
No,
No?
we almost drove off the road.
Okay, good. That's good to know. All right. Oh, yeah.
The secondary rainbow always on the outside of the primary?
Yes. Yeah. Because the light reflected, it ends up being reflected at a larger angle because of the 2 reflections. And also the colors are reversed. Yeah.
Yeah.
Let me go back to that picture. Do I have a double rainbow? So kind of here on the previous one. Oh, wrong direction.
Wrong direction. Come back, little Sheba.
I'm trying.
Video for us. There.
Okay. Yeah. So you'll notice the colors are reversed. Red is on the outside of the rainbow for the primary rainbow, but it's on the inside of the rainbow for the secondary.
Why is that?
Because when you look in a mirror, when you're reflected, your image is reversed. But if you were to look in two mirrors, your image would be reversed again. So because the light's going through two reflections, it's reversed from the first reflection. Going through multiple lenses on the camera. You mean the camera that took this picture?
Yeah.
Unless you have a really crappy camera lens, it shouldn't be dispersing light into its colors before it hits the photographic sensor. So no, it's not because of the camera lens. Wait. Yes. Yeah, so the third rainbow, if it's visible, would have the same color distribution as the primary rainbow. All right, let's move on. Rainbow connection. Come on. Come on. You can do it. I don't know why this is being so finicky, Dave. All right, there we go. Sundogs. This particular photograph is spectacular. This captures in a photographic image several different phenomena related to the sun. And these are phenomena that you typically only see on cold days. So this is probably not taken from Florida. And you've got the line that sort of comes in from the edge of the picture and goes off the other edge of the picture. That's like a loop that can actually circle from from the sun to the other end of the horizon, the antipodal point in the sky, because the ice crystals that form a lot of these, if the air is still, the crystals will typically orient themselves to be horizontal. And remember my talk about water and ice from a few months ago? Hexagons and hexagonal shapes are the shapes fundamental to ice crystals and snow, right? So you get these little plates, these hexagonal plates of ice crystals that are parallel to the horizon, horizontal, and they reflect the sunlight back down to you. And so you can get these wonderful phenomena where you've got these multiple reflections that form different kinds of rings, depending upon the specific geometry of your orientation with respect to the sky and the sun. And then way off to the side, you see these colored bands in the clouds. Now, if you'll notice, the red is on the outside, just kind of like the rainbow, right, on the upper loop. And that's because of sunlight refracting and reflecting through ice crystals instead of water droplets, typically. So you'll see these kinds of sundogs where you see bright little snippets of rainbow colors on either side of the sun. You'll see that during the fall and spring when the upper atmosphere tends to be colder. Clear and cold days, low sun to the horizon. That's always when to look for most of these phenomena is sunrises and sunsets. And optimal conditions are when the sun is between 22 degrees and 45 degrees above the horizon. So something kind of like, I don't know, 22 degrees is kind of like that, and 45 degrees is something kind of like that. And this kind of shows the light can be refracted and reflected inside of ice crystals, or it can reflect off of the ice crystals as if it were just a mirror. And that's what led to that complex interplay between light and ice crystals in the atmosphere that you saw in that first image a minute ago. Right. You can actually see rainbows at night very occasionally. And they're formed by the light of the moon. So if the moon is full and bright and behind you, and there's mist up ahead of you, then you can see a rainbow at night. One of the other things you can occasionally see is sun pillars. These are pretty awesome. You'll see these fairly frequently, even around here. We're not in the Arctic, as far as I know, and we can pretty frequently see sun pillars caused by ice crystals in the atmosphere. So typically not during the heat of summer, but fall and winter is a great time to see some of these more interesting optical phenomena due to ice crystals in the atmosphere. And here we see a sun pillar accompanied by sun dogs. And I've seen something like this a few times. I don't leave the house very often, so I'm sure it happens more often than I know. All right. And then whoever it was that asked about the full circle, occasionally you can see a full circle of around the moon. You're not likely to see this around the sun because the sun is just too bright, and don't look at the sun. So even if it were there, you'd never know. But around the moon, you'll occasionally see just a circle of light because in this case, your eye is in the path of the water droplets, and then beyond it is the source of light, and so the light's coming at you like this way instead of from behind you, and you can see a ring of rainbow colors more frequently because of the size of the water droplets or ice crystals involved. The Mie scattering causes the ring just to be glowing, right? It's just you don't see color differentiation within it, and their moon rings are frequently associated with ice crystals way, way up in cirrus clouds. And meteorologists know that cirrus clouds are often a precursor of a weather front that moves through. So you'll get the high cirrus clouds moving through, and then after that you'll get the ones that are more loaded with moisture and thicker, bigger clouds. And so it's an old wise tale, or is it wives' tale? Wives' tale, I think. That if you see a ring around the moon, it means a storm is coming. And there's some scientific plausibility to that piece of folk knowledge. So here's a picture of you can actually see a double rainbow, and this is caused by the moon. So the green is not part of the rainbow. That's a whole other thing that we're going to talk about next. Electrical phenomena in the Earth's atmosphere. This is an actual photograph of aurora happening in the way upper atmosphere. Aurora, the phenomena that causes aurora is way above where storm clouds live. The storm clouds and whatnot live in what's called the troposphere, the thicker part of the air down near us, the air we can breathe essentially, and that's where weather happens. And then way, way above that, kilometers or miles, many miles, tens or 50 miles or so above that, is where the particles from the sun hit the atmosphere and excite these gas discharges. Friction. Anytime you get friction happening in the atmosphere among tiny particles, you're likely to get lightning. Just like, somebody was wanting to remind us of touching a doorknob or rubbing a balloon in your hair, static electricity, you're stealing electrons from one place and loading them up on another place. But if you get a lot of friction happening in bulk in the atmosphere, you can get lightning. And so we see lightning striking in front of this wonderful downburst here coming up on Chicago. And then this is, I believe, from the Chicago Tribune, this picture. And I believe this other picture is from the National Geographic, showing you don't have to have rain clouds. You can get lightning in clouds of smoke and ash. This is lightning happening in the plume of a volcano. Right, kind of explaining a little bit about lightning. Lightning can go from cloud to cloud. It can go from cloud to ground. As the ice particles and water particles are wafted up in the atmosphere, they bump into one another, and that is friction, right? That causes friction, and so they can become charged. and you get this distribution of charges between the very top of a cumulonimbus storm cloud and the towards the bottom you get the negative charges, and then at the very bottom you might have some positive that's and then on the ground you get positive. You get this separation of charges between as electrons sort of stream through the atmosphere and among the particles, and that's what builds up a static charge that results in lightning. And lightning is where the electrical, essentially the resistance of the atmosphere, the nitrogen and oxygen is overcome. So nitrogen and oxygen make good resistors. They're not typically good conductors, but you overcome that resistance with enough current, like you can do with really any resistor. You put enough current through it, enough of a voltage potential across it, and that dielectric material will break down and conduct electricity.
Do you happen to know what causes one particle to pick up a positive charge and another particle to pick up a negative charge?
I don't. Last I looked into this, probably, I don't know, 5 years or so ago, it's an active area of research, at least it was 5 years ago, about exactly how the mechanism of building up charges and dispersing charges in a cloud. That's it's something that happens all the time in nature, but we scientists, as far as I know, don't yet know all of the details about how it happens and the mechanism behind all of it, and the interaction with air particles versus ice particles versus water particles versus air currents and whatnot. It's very complicated. My short answer. Come on. There. So this is a map spanning from 1993 to 2003, showing lightning strikes across the world. Red, so that's the key over there. Purple is fewer lightning strikes, and dark red is more lightning strikes. So the Congo is just hammered with lightning, typically. A lot of moisture there, a lot of air currents, a lot of clouds and whatnot. It's the jungle, right? Same thing in Borneo and Indonesia, the islands over there where there's jungle in Asia. You'll see a lot of lightning. And then up there in Venezuela and in South America, the tip of South America, or the top of South America, again, a lot of jungle. So a lot of moisture in the air, a lot of storms, a lot of lightning. Okay, so I want to talk about these things called sprites. This is a picture of one right here. So remember I talked about the dielectric constant of nitrogen and oxygen. When that dielectric constant is overcome by a huge charge, you get a discharge and you see light. Well, in the upper atmosphere, that dielectric constant is a lot lower. It takes less charge, less current to overcome the resistance of air rarefied in the upper atmosphere. And you tend to get these flows of electrons. It's not so much a lightning bolt that happens in a fraction of a second as it is sort of a current of electrons. And it's more akin to what you would see in the discharge of an electric or a neon light. And here's a photograph of one. So in the distance is a storm. So this is a storm cloud. So the same sort of electrical differentiation between positive and negative is happening in this storm cloud, and the photographer is far away from the storm, but far enough that he can see many tens of kilometers above the storm. He can see this flow of current exciting the nitrogen in the atmosphere, and much cooler. You know, it's not the millions of degrees that a lightning flash would be. It's a much gentler flow of electrons, but it's the same kind of effect that you would see in a tube with rarefied gas in it. Yeah, it's beautiful, isn't it? I've never seen one.
Is that a time-lapse photograph or is that instantaneous?
I believe this is a short time lapse, something like 30 seconds. So they're very dim, hard to see with the unaided eye. Beautiful, one of the most beautiful electrical phenomena in nature. Looks like a jellyfish floating above the sky. Huh?
That's definitely a wow.
Yeah. Okay. Whoop.
You almost had it.
All right. So that happens in the ionosphere. Let's see, where am I? Or no, it happens up in the thermosphere and the mesosphere. So those of you who haven't memorized the layers of the atmosphere and the way we name them, here's a helpful reminder. So the troposphere is where airplanes and weather occur. And then the stratosphere, you've heard about that. That's where weather balloons go. And then as the atmosphere gets more and more rarefied up to the exosphere, which is outside of Earth's atmosphere, the sphere. So exosphere is space. It's a fancy name for space. So these happen way, way up there, way above storm clouds. And then occasionally you'll see what are called elves, this just ring of light around, typically green light around where the these red sprites are. And occasionally you'll see just a burst of current, a flow of current that's not as chaotic and fractal as a lightning bolt, called blue jets that come out of the top of a storm cloud. So you'll get elves and jets and sprites. It's like a whole fairyland up there above the clouds. There are also phenomena I'm not going to talk about today. I'm getting to run out of time, and I didn't put them in the slides anyway. Ghosts, gigantic jets, pixies, gnomes, trolls. See? Fantasyland. All right, now we're on to talk about Steve. It's rare to have a weather phenomena named after oneself. And yeah, just stealing my punchline here with the clicker not working. All right, this is Steve, actually. The other thing was also a Steve, but this is called a strong thermal emission velocity enhancement. Duh, right? We could have figured that out. This is Steve. It usually happens under the similar conditions to when aurora happen, when the northern lights happen. And it's just a flow, like a channeled flow of particles into the atmosphere. And it's this long swooping swath of light in the sky. This has been observed for centuries, and probably longer than that. It was first recorded centuries ago, but it was given its name in 2016 by a group of sky watchers in Alberta, Canada. Those clever Canadians. Steve is a narrow band of pink or purple light, seen often alongside aurora. And in case you want to know where the ionosphere was, you'll probably remember that it wasn't in that other picture. See? Yeah, testing your memory. The ionosphere is sort of a combination of what happens when molecules are easily ionized when electrons are knocked off of them in the mesosphere and the thermosphere. Kind of straddles them. All right. And then speaking of aurora, so charged particles from the sun stream outward into the solar system. Some of them end up coming towards Earth. And then the magnetic field of the Earth sort of funnels the charged particles towards the poles. And when those charged particles hit the poles of the Earth, either the northern or southern pole, magnetic pole, it causes an interaction of the charged particles with the atmosphere, and it can also cause kind of a neon glow effect. Only this time it's nitrogen glow and oxygen glow primarily. And the typical arc or circle of the aurora, it's aurora borealis if it's north, aurora australis if it's south. This is an image of during a pretty robust aurora outbreak. So Alaska and northern Canada would have a good view of the aurora here, where the image tends towards orange. And this is the kind of thing they'd see in the sky. And if you're up here in northern Minnesota, where I've been a few times, there's a pretty good chance typically of being able to see the aurora if you're up in these areas, northern Maine, Minnesota, certainly Alaska, maybe Washington State, etc. And they're northern lights. We live in the northern hemisphere, and we see them in the north. But occasionally, like has happened a couple times this year, this happens. And this is a storm. So the sun has puked out a huge number of particles. Sorry for the graphic description. Yeah. And a lot of those charged particles a huge number hit the atmosphere, and it can cause these outbursts. A solar storm is what this is called. Even though it happens on Earth, it's called a solar storm or an aurora outburst. And you'll notice, if you look carefully, that northern Illinois is right here. And this happened twice this year so far. The first time it happened, which was May 11th, 2024, it was cloudy here. But the second time it happened was at the beginning, right in the middle of October, right? And this is a picture I took. This is a picture from Yorkville, Illinois. So they were visible here, and they're just curtains of light, coruscating curtains. You can see them moving minute to minute, right? Gorgeous stuff. It gives sprites a run for their money, at least. Come on. And there we go again. I'm trying. I don't know why this is being so uncooperative. There. So the different colors of aurora. So you'll see green and red and maybe blue and pink, depending upon where you are in relationship to the aurora. But this, if you want to give this a quick once over, this explains how the electric currents interact with different molecules in our atmosphere to create the different colors. I'll go through the list with the arrows real quick. Red, up at the top of the aurora, is typically charged particles interacting with O, just monatomic oxygen. Yellow and green is happening with a combination of the way oxygen and nitrogen molecules bounce off of each other and exchange electrons lower down in the aurora, and that's typically the bulk of the color in auroras that you see is yellow-green. You can get a rare spectacle of blue aurora, which is charged nitrogen N2 ions. And then deep red is just neutral diatomic nitrogen, N2. And then when you get reds and blues and greens interacting with each other, you can create all kinds of different colors, pinks and other pastel colors. So it really is spectacular. I recommend, if you've never taken a trip to Iceland, which is a relatively inexpensive airfare for in the grand scheme of things, try to go there during the winter or fall. So aurora tend to be more prominent in falls and springs because of the way the Earth's magnetic field tips and aligns or doesn't during other seasons with the sun's magnetic field. And that's what I had for today. So these different phenomena here, many of them on one slide, talking about these beautiful things you can see in the atmosphere. And now you know more about why the sky is blue and purple and green and all these other colors. Thank you very much.
And pixies and sprites.
Yeah, I'm willing to entertain questions or discussion.
Have microphone. We'll travel.
All right. Thanks for coming. I don't know what Mike's topic is going to be in 2 weeks, but I'm sure we will all be delighted by it. He does a great job, and hope to see you in 2 weeks at the next Science Sunday.
Thank you.